Romantic comedy or action?
I don't do or. Or makes you choose. I want romaction. Cyborg meets his baby mama. Who wants or? I'm done with or. Hit me! Or! Huh! Yeah! What is it good for? Absolutely
Coke Zero.
nothing.
Real Coke taste and 0 calories. Enjoy everything.
Alright, welcome to section 5.2. Today we're going to be talking about polynomial division and the factor theorem and how we can use these two processes to help us find zeros of polynomials. That's why I kind of played a Coke Zero commercial at the beginning. We're going to be taking a look at zeros on a graph, and more specifically, remember those are the x-intercepts. So just as a refresher in long division, I'm pretty sure we did this in Algebra 2. The first piece is our dividend. That's what goes underneath our division bar. And the second piece is our divisor, what's on the outside. Now we gotta be careful because if you take a look at the initial setup, notice how I kind of threw in some zeros in there because they weren't really showing up in our original dividend in this case. We're going straight from a degree of 4 down to a power of 1 over here, which means we're missing the degree of 3 and that degree of 2 in our standard form equation. So if we're missing those pieces, we got to make sure we put them in as zeros or placeholders in order to help us go through this long division process. So in order to go through the long division process, we're always focusing on our first terms in this case. The rest will kind of fall into place, so we're just going to take a look at the first two. We're going to take this 2x to the 4th and divide it by the x squared. So we're taking this first term divided by this first term, which is going to give us a 2x when we do that division. So this is what actually goes as the first piece of our quotient, or in other words, the answer when we divide. Now, if you remember back from middle school or elementary school when you do the long division process, as soon as you put something up top, we need to multiply it over to our divisor. So 2x squared times x squared is 2x to the 4th. 2x squared times 2x is a 4x cubed. And 2x squared times 1 is 2x squared. Now in the division process, we always subtract, so let's go ahead and see what happens. Notice how the first terms cancel. That's good, that's what we want to happen, and we'll go on from there. So our placeholder 0 minus 4 gives us negative 4x to the 3rd, and our other placeholder 0 minus 2 gives us a negative 2x squared. Notice how those are important because we actually are using them when we go through this subtraction process, so we can't forget those placeholders. Just like in normal long division, we always bring down the next term, and we continue the process. So again, taking a look at this first term and our new first term, if we do negative 4x third divided by x squared, we're going to get negative 4x. So that's our next term in our quotient. Multiplying it over, we get negative 4x to the 3rd minus 8x squared minus 4x, and again we are always subtracting. And it's important to remember we're subtracting because notice how when we take negative 4 minus negative 4, this is essentially changing to a plus, which means those are going to cancel because one's negative and one's positive. So we got to be careful with this idea of subtraction. Negative 2 minus negative 8, this is going to change to a plus as well, so we're left with 6x squared. And then 3 minus negative 4, this is going to change to a plus, which means we're left with 7x, and we can bring down our next term. And the process continues. So we have x squared divided, or 6x squared divided by x squared, which is just going to give us a value of 6 because those cancel. So we can put 6 up top and multiply it over to give us 6x squared plus 12x plus 6, and again we're going to subtract. First terms cancel just like we want. 7 minus 12 gives us a negative 5x, and then negative 1 minus 6 gives us a negative 7. Now we can't go any further because the degree in our divisor is larger than the degree in what would be considered our remainder. Notice how the degree is 1. So there's no way we can take a degree of 1 and divide it somehow by a degree of 2 because we're not going to be left with something nice like we've been having in these cases. So that's as far as we can go. We can't go any further. So what we can do is actually write our solution. We can write our quotient as a summary statement. Here's our quotient. We had 2x squared minus 4x plus 6. But we need to add our remainder on the end, and the remainder we have is negative 5x minus 7, and it's specifically out of the divisor that we were using, this x squared plus 2x plus 1. So we can say after this long division process, here is our quotient, here is our answer. What I want you to do is take a second and try number 2 on your own. Alright, check it out and see how you did. We didn't have to worry about any placeholders in this case because notice how we go from a 3 to a 2 to a 1 and then to nothing at all, or no x's in this case, that's our constant, so we don't have to worry about any of those placeholders. So when we go through the division process, remember that we are subtracting in all of these cases. Make sure you're subtracting your numbers correctly. We're left with a quotient of 2x squared plus 8x plus 9, but we have a remainder of 1, which gets added on to the end, and it's divided by our original divisor, this 2x plus 7. Hopefully we did really well in this case. I think this is a review. If it's not, just let me know if you need some extra help. So we're going to talk about a different type of polynomial division. Instead of the long division kind of taking up a lot of space and a lot of work, I find it that students really like synthetic division. And before we actually get to synthetic division, we're going to talk about synthetic substitution. So in this case, we have a polynomial function 2x cubed minus 5x squared plus 10, and we specifically want to find the value of our function when x is 3. Notice how the 3 is just taking the place of the x. Now you could simply just plug in 3 for all of your x's, maybe in your mind or in your calculator, and notice how if we were to do that, we would get a solution of 19. So we know if we were to plug in 3, our answer would be 19. But there is a synthetic way of doing this without having to use your calculator, and maybe plugging in 3 would give us some large numbers that we really wouldn't want to use, or wouldn't be able to use really easily, at least in our heads. So going over synthetic substitution initially, this 3 value that we're specifically looking at goes on the outside of this setup. So we're going to put this number 3 right here, and we're only going to use the coefficients of our function, in other words 2, negative 5. Notice how we would have to use 0 because we do not have a single x, and then we could use 10. So the placeholders still apply in this case. So it's synthetic because we're not really concerned about the variables, at least just yet. Now in terms of using synthetic substitution, here's the process we kind of use. This first number you put down here, in this case 2, gets dropped below what we would call this division bar. So we drop our first number. Then we take this 3 on the outside and multiply it by 2, which would give us 6, and that's exactly the number we put underneath our next coefficient. So now that we have negative 5 and a 6, we're going to add them together to give us a 1, and the process continues. So we're going to take 3 times 1, which is 3, put that underneath our next term, which is 0, add those together to give us 3, and the process continues again. If we take 3 times 3, that gives us 9, 10 plus 9 gives us 19, and we are done with our synthetic substitution. And notice how this last number matches exactly what we got in this case when we used our calculator. So it may not be the most efficient method of using substitution. Okay, you can just use your calculator or plug it in for x's in your head, but it is another way of substituting. Now this process though we are definitely going to use when we talk about synthetic division, so I want to just take a second and show you how that works. I want you to pause the video and try number 4 on your own. Alright, so if we check it out and see how we did, our x value of 2 goes on the outside, and we're just looking at the coefficients in our polynomial for our other terms here. So we'd have a negative 5 and then a 1, but notice how we're missing our x squared term, so we would need a 0. We have a negative 3x, but we're also missing our constant term, which means we would put a 0 in there as well. So we got to use those zeros for the pieces that are missing as placeholders to help us out, because when we go through this synthetic division process of dropping the first number and going through and doing the multiplication and addition all the way through, it looks like we should get a solution of negative 82. And if we want to check it, just to make sure we did our synthetic substitution correctly, we can do negative 5, put in negative 2, raise it to the 4th, plus a negative 2 to the 3rd, and then we're going to subtract 3 times negative 2, and our solution is negative 2, just like we got in this synthetic substitution process. Alright, so now that we know how synthetic substitution works, we're going to talk about synthetic division, and it's basically the same thing, but we use synthetic division when we are dividing by a linear binomial, meaning when our divisor looks like a line mx plus b. Okay, we would not have been able to use synthetic division in this case, because notice how our divisor was quadratic, okay? It was x squared plus 2x plus 1. Now we could have used synthetic division in this case because this divisor is a line and looks like mx plus b, but that's the only time we can use synthetic division, when it looks like we're dividing by a line, mx plus b. So in this case, we're dividing by a linear binomial. We have n minus 3. And what's tricky about this is we got to figure out what's that number that goes on the outside of our little division box over here. And we specifically are using the 0 of our divisor. So if we were to set this equal to 0, the specific n solution would be 3. So that's the number that we put over here. That's why I played the Coke Zero commercial at the beginning. We got to find our 0, at least in this case, of our divisor. So we would put a number of 3 on the outside, and then we can use the coefficients of 2, negative 10. Notice how we're missing an n squared, so we got to put in a 0, and we can use 30 and then 28. So when we go through this synthetic division process and do our multiplication and our addition all the way through, let's see, 3 times negative 12 is negative 36. Add that to 30, we get negative 6. 3 times negative 6 is negative 18. And add that to 28, and we get 10. Alright, so here's how we read. This is essentially our quotient down here, and we want to read it very specifically. This last number, I always try to box it off, is representing your remainder. Okay, so this is how much you have left. But these other pieces are the coefficients of the n variables in your divisor. And this 6 is specifically representing a constant. Okay, this is just going to be a number. This negative 12 is representing how many x's you have. This negative 4 is representing how many x squared you have. And this 2 is representing how many x cubes you have. Now if we had more numbers, we would just continue our pattern, but notice how we always start off here with our remainder and kind of work backwards. So in the end, our quotient in this case would be 2n cubed, because our variables were n's. I mean, you could use x's if you wanted to, but we would have 2n cubed minus 4n squared minus 12n minus 6. So we're using these coefficients and what they represent to help us write our quotient, but we always need to add our remainder over our original divisor, and that was our n minus 3. So that's our synthetic division process. It goes a lot quicker. Notice how it takes up a lot less space. I think students really like this better than that long division. Alright, so let's take a look at our second one. We got to find the 0 of our divisor. So if this were to equal 0, what would our x solution be? Well, we would subtract 3 and then divide by 2, so we would be left with a negative 3/2. So that is the number that goes on the outside of our synthetic division symbol. Then we can use our coefficients of 2, negative 5, and negative 12 to help us out. We don't really need any zeros in this case as placeholders, so we're good to go. So if we drop our first number 2, negative 3/2 times 2 is negative 3. And when we add that to negative 5, we get a negative 8. Negative 3/2 times negative 8 is a positive 12, and when we add that to 12, we get 0. Alright, so this is representing your remainder, this is representing a constant or a number, and this is representing how many x's you have. Now, according to this, our divisor, or sorry, our quotient, our answer, would be 2x minus 8. And if we were to add the remainder, we're essentially adding 0, which doesn't really change anything. So this is all we really need. This is our quotient. But this is what's really particular and tricky about the synthetic division process. Okay, this original linear equation, notice how it had a slope of 2. Okay, this slope of 2 is what we need to divide our quotient by. So we're going to divide our answer, absolutely everything, by 2. Almost like how we would take that a value when we would factor and divide that by our 2 numbers that we found that would multiply and add. Very similar to what we're doing here. Okay, so this is what's tricky. When you have a slope, notice how this one was 1, so that doesn't really change anything when we divide by 1. But if we have a slope in our linear binomial, we have to divide our quotient by that. 2 divided by 2 would give us a 1x, and a negative 8 divided by 2 would give us a negative 4. So our actual quotient is x minus 4. That's the one little tricky thing about using synthetic division. You gotta watch out for that slope. Alright, so 2 important theorems that we have that are going to help us find zeros of polynomials, okay, find those x-intercepts. The first one's what's called the remainder theorem. So if a polynomial f of x is divided by x minus k, now this k is just going to be a number, okay, any other number, then the remainder r is the answer when you plug in k into your function. That's what this is saying. When you plug in k into your function and for your x value, you get an answer of r. So for example, let's say we're taking a function and we were dividing it by, I don't know, x plus 7. Okay. If we were to put in negative 7, notice how it's kind of that opposite, because when we set it equal to 0, if we were to set this one equal to 0, we would subtract the 7 over to get negative 7. If we were to put in negative 7 into our function, whatever that answer is the remainder if we were to do this division process. So this is going to come in handy in the next few examples as a shortcut to test whether or not that this x minus k can go evenly kind of into our polynomial. Okay, does it have a remainder or does it not? And that's what kind of clues us into this next theorem, is the factor theorem. This x minus k is a factor if the polynomial function, if we get a remainder of 0. So again, if we were to plug in negative 7 and get an answer of 0, that means that this factor, x plus 7, evenly divides into our polynomial. And that kind of makes sense, because if we think about it in number terms, if we take 12 divided by 4, we know our answer is 3 because we have a remainder of 0. So 4 is a factor of 12, but also 3 is a factor of 12. Notice how 4 goes into 12 evenly. We don't have a remainder. So when our remainder is 0, when we get an answer of 0, we know that these two pieces, okay, our divisor and our quotient, are factors of our original number, or in this case, our original polynomial that we're starting with. Sometimes it's hard to understand those theorems when they're written in words, so I think looking at an example will really help us try to understand or really start to realize what these theorems mean and how they work. So given one zero of a polynomial function, we want to find the other zeros. So we know that 3 is a 0. Okay, we can actually test it. If we wanted to put it into our calculator, we could put in, this will work. If we put in 2 times 3 to the third, and then minus 20 times 3 squared, plus 33, or 66 times 3, minus 72, we get an answer of 0. So we know that this 3 is a 0 because the remainder is 0. We got an answer of 0 when we plugged it in. So that tells us that x minus 3 is a factor. Okay, this factor is evenly going to go into this polynomial. Now again, we're using the opposite sign. So if this is a positive 3, we have a minus 3 in our factor. So if this is a factor, we can divide it into our original polynomial to help us find the other factors, since it evenly goes in. So you can use long division, you can use synthetic division. I'm going to use synthetic because I think it's a little bit quicker. So we put our 0 on the outside, and we're going to use our coefficients of 2, negative 20, 66, and negative 72. We drop down the first term and continue through our synthetic division process. And notice again how we're just reiterating the fact that our remainder is 0 because that's what we get as our remainder when we go through our division process. So our quotient is 2x squared minus 14x plus 24. So since we know that this x minus 3 is a factor, because it goes in evenly, this, oh my gosh, this quotient, sorry, lost my thought process right there. This quotient is a factor also. Just like in our last example, if 4 goes in evenly, 3 goes in evenly as well. So we want to factor this to help us find the other solutions, or our other zeros for our graph. So we can maybe factor out a 2. And it looks like we can factor our inside a little bit further. Two numbers that multiply to 12 but add to -7 are -3 and a -4. So our two other solutions for x would be a +3 and then a +4. So overall, this polynomial function has 3 zeros. Okay, it has 3, our original 0. It has this other solution of 3, so it kind of shows up twice. And then it has this solution of 4. So it had 3 overall zeros, and just a little hint coming up, notice how our original degree was a power of 3 as well. So these ideas are very much related. Okay, the fact that we had original degree of 3 kind of clues us in that we should be getting 3 answers. We should be getting 3 zeros when we go through this division process. Alright, so let's just check out another one for some practice. Given our polynomial function, we know 1/2 is a 0, so we know that x minus 1/2 is a factor, but we're not really used to seeing it written as a fraction. Remember, we always try to move that denominator over as a coefficient, so we would say 2x minus 1 is a factor. So we know that if we were to plug in 1/2 for all of our x's, our answer would be 0, meaning that our remainder is 0 when we go through the division process. So let's set up maybe synthetic division. You can always use long division if you're more comfortable with that. I'm just more comfortable with this one. And it doesn't look like we need any placeholders, so we'll just go through our process. So continuing through, half of -16 is -8. We get 82, half of 82 is 41, and our remainder is 0, just like we should anticipate because this is a 0. 1/2 is a 0, so our remainder should be 0 because it goes in evenly. So our quotient is 2x squared minus 16x plus 82, but hold the boat, okay, we gotta be careful. Notice how our slope and our divisor was 2. Okay, we're using the synthetic division process. We gotta be careful with this slope. We need to divide everything by 2. So that would give us x squared minus 8x plus 41. Alright, so just like before, this is a factor. This goes in evenly into our polynomial, just like this 2x minus 1 would, because we got a remainder of 0. So we want to try to factor this to find our other solutions, but there really aren't any numbers that multiply to 41 but add to a -8. So if factoring is not an option, we always go for that quadratic formula. So if we think about the opposite of b, plus or minus the square root of b squared minus 4 times a times c, 41, all over 2a. I believe when we go through the process, you can simplify the square root. Maybe it might, oh, it is going to be imaginary. Imaginary number, divide everything by 2. Our x solutions would be 4 plus or minus 5i. Alright, if you actually need help from me to simplify it to that, just let me know. But there's our solutions. So again, let's take a look at this little hint here. Our degree was 3, which means we should have 3 solutions. We're kind of running out of room on this slide here. Okay, so we should anticipate 3 zeros. We should have 3 answers. The first one was given to us. We have 1/2. But we also have 4 plus 5i. That's one solution. And then we have 4 minus 5i. That's another solution. So our degree of 3 is cluing us in that we should have 3 answers. And that's kind of a good way for us to check our work, because if we can only get 2, or if we happen to actually get 4, we know we did something wrong. So notice how they can be imaginary solutions, they can be imaginary answers. That's completely okay, because we're just trying to find the solutions for x that would work in this particular polynomial. Alright, so a good thing to ask ourselves is, if we know x equals 3 is a 0 of a function, what else can we actually know or conclude from that fact? And we can actually conclude 3 very specific things about this idea of a 0. If x equals 3 is a 0, we already know that x minus 3 is a factor. Okay, it's going to go in evenly into our function, and we use that idea on the 2 previous examples actually. Now something else we know is that if x equals 3 is a 0, then x equals 3 is an x-intercept. Okay, 0 and x-intercept mean the same thing. Okay, they're just 2 different words. Mathematicians like to use different things because mathematicians come from all over the world. They use different terminology. But a 0 and x-intercept mean the same thing. And we also know that x equals 3 is a solution to the fact that our function is equal to 0. So notice how if it's a 0, if it's a factor, it goes in evenly. If we were to plug in 3 into our equation, we should anticipate an answer of 0 because it's a factor. It goes in evenly. So we can conclude these 3 different pieces just from this single statement. Alright, so let's take a look at one more example. Given the graph of this particular function, if you were to put this into your calculator, you would get something that looks like this. And notice how I give you the window just in case if you want to check your graph, you could actually do that. And we're going to use our knowledge of the factor theorem to find the exact values of all the zeros. Okay, in other words, those x-intercepts. So it looks like there's an x-intercept, and there's an x-intercept, and there's one, and there's one. And notice how we have four zeros, okay, 4 answers, and that makes sense because our degree is 4. Alright, now the thing is, in order for us to start to find the exact values of all of these, we need to know a beginning 0, because all of the other examples we talked about, they kind of gave us a 0 to get us started. So we need to find a 0 first in order to help us out. And that's where we're going to take a look at this graph. Okay, we want to find a nice 0 to help us out, and I'll always give you a nice one. This one isn't nice because notice how it's a decimal, it's kind of in between those values. This one is going to be a decimal as well. It's kind of in between 0 and -1. This one's a decimal too. It's in between 1 and 2. But this one is nice. It's actually on a value of 3. And you know that because I give you the scale of the x-axis here. So we already know that x equals 3 is a 0. Okay, which means that x minus 3 is a factor. So this is going to go in evenly into our function. So maybe we'll use synthetic division. If x equals 3 is a 0, that's what we can put on the outside. Using our coefficients, make sure we don't need any zeros, and I don't think we do. We can go through our synthetic division process, adding and multiplying as we go, checking our work just to make sure. Ooh, that should be a 3. I didn't check my work. There we go. The -9 should go down there, which would give us -27, and then a -3, -9, and add it together gets 0. So it's good that we get 0 because we know that this x minus 3 is a 0. Okay, we found it on our graph. So that means that this other quotient numbers here are representing our answers. So we would have 3x to the third, actually, plus 1x squared minus 9x minus 3. Remember, this is a number, this is representing an x, this is an x squared, and this is an x cubed. So here is our quotient. And since the x minus 3 goes in evenly, notice how it has a remainder of 0, we know that this quotient goes in evenly as well. So we should be able to factor it to find our other solutions for x in terms of their exact value. So notice how we have 4 terms here, which means we can group our first 2 and group our last 2. Out of our first group, we can take out and x squared. So we're left with a 3x plus 1. And I specifically want to factor out a negative 3 from my second group. That way I'm left with a 3x plus 1 in order to match this. So our two factors, I'm going to write them over here, would be x squared minus 3. Okay, the items we pulled out or factored out. And then the 3x plus 1 that they both have in common. Alright, so now that we found the factors, we can find our solutions for x. So either this x minus 3 equals 0, because remember this quotient is a factor, it goes in evenly, it should equal 0, or this piece equals 0 as well. So if we add the 3 over, we'll get 3, and taking the square root of both sides, we'll have plus or minus the square root of 3. Over here, if we subtract 1, we'll get negative 1, and then divide by 3, we get negative 1/3. Alright, so our four solutions, our 4 zeros, we would list them maybe down here, zeros. And they said they want them in smallest to largest, so we'll try to do that. Looks like the smallest one would be a negative square root of 3, because the square root of 3 I think is like 1.7 something. Then the next smallest would be our negative 1/3. Okay, that's the solution here. Now, the next smallest would be a positive square root of 3. But then our last one was the original one we found at the very beginning. Okay, we can't forget about that because this one helped us do the entire process. So our last one right there would be a positive 3. And those are the exact values of these other ones on our graph. Looks like we have negative square root of 3 right here. We have negative 1/3. We have a positive square root of 3, and we have 0. So last but not least, we're going to end with the fundamental theorem of algebra. And it's kind of crazy that you guys are all the way here, and we're only getting to the fundamental theorem of algebra right now when you've already had Algebra 1 and Algebra 2 before. But the fundamental theorem of algebra specifically states a concept or something that we noticed in this lesson. If a function is a polynomial of degree n, then the function, or then the f of x function equals 0 has exactly n solutions. So this is telling us that if our degree is n, we specifically have n solutions when our graph is equal to 0. Or in other words, we have n zeros, or in other words, n x-intercepts. So just like before, the degree of our polynomial is telling us how many answers or solutions or x-intercepts we should have. Now, they might not always be real. Okay, we could have some imaginary solutions, but we could just have all real solutions. It just depends on your graph. For instance, if we just quickly think about a cubic, for example, something that looks like this. This is an example of a cubic function. There might be some other terms to it, but it has this general shape. Based on the cubic, we know we should have 3 zeros. We should have 3 solutions. But specifically on our graph, we only have 1 real one. So this is telling us that since we only have 1 real solution, we can anticipate 2 imaginary ones, because this is telling us how many solutions we should have in all. Okay, they can be real, they can be imaginary, they can be all real, all imaginary. It just depends on your graph. So something we noticed before, the degree is related to how many solutions you should have. Now, something else that kind of tacks onto this idea when we're dealing with imaginary solutions is that imaginary zeros will always come in what are called conjugate pairs, meaning that each imaginary zero will have a conjugate buddy, if you want to think about it in that case. So there won't just ever be one conjugate solution. Okay, they always come in pairs. So we talked about the idea of a conjugate in the last lesson when we talked about differences of squares. The idea of a conjugate is when you keep the terms, but they differ in sign. So for instance, in this one, we have a real number 3 and an imaginary number of a positive 2i. If we were to find the conjugate buddy, we would still keep the 3 and the 2i, but it only differs in sign, or sorry, not sign, in operation. So instead of adding the real and the imaginary together, we would subtract the real and imaginary together. So that would be this conjugate buddy or conjugate pair. Now in this case it's a little tricky, because notice how the imaginary number comes first and the real number comes second. We want to rearrange this so that the real number comes first. This is what a complex number actually looks like, where the real number comes first and the imaginary is second. So if we were to rearrange this, it would actually look like negative square root of 5 plus 7i. So this is an imaginary solution. We want to name the other solution. Well, we would keep the negative square root of 5 and we would keep the 7i, but instead of adding them together, we would subtract them. So we got to be careful because a lot of us, I think, would just take a look at this and want to change this operation from a minus to a plus, but that's not actually what's going on here because the imaginary and real terms were switched. Okay, we got to make sure that the real part comes first, and notice how it kind of changed our problem in that sense. So good luck on the practice, good luck on the application, good luck on that mastery check. This section can be kind of difficult, so don't be afraid to ask for help. I'll see you guys later.